Well, hello. Thank you all for dialing in. This is Balancing Tradeoffs, implementing realistic adversary TTPs without breaking the bank. So, my name is Michael Long, and let me say I'm so thrilled to be presenting virtually as part of Cocoon's Adversary Village. So, what is this talk about exactly? In a broad sense, this is about realistically implementing adversary TTPs while also balancing those real world project constraints that we all face, things like limited time and budget. As we go forward in this talk, I'm going to share with you insights and techniques I've gained over the years as we grapple with implementing realistic TTPs and balancing these finite resources in the real world. So here's our agenda. I'm going to start by talking about what it means to implement adversary TTPs. Why do we do it? What goes into it? What does a TTP implementation actually look like? Next, we'll talk about the key problem statement that is really the subject of this presentation, which is how do we practice realistic adversary emulation while also balancing limited time and budget? As we go forward, I'll share with you tips for how I plan TTP implementations with those constraints in mind. And finally, I'll share with you several approaches and real world examples showing how my team addresses this problem in our day to day work. Now, before we dive in, let me give you a quick intro. Again, my name is Michael Long. I'm an adversary emulation engineer at a company called MITRE. Now, most of my daily work entails emulating adversary tactics, techniques, and procedures, usually done with the goal of assessing and improving cybersecurity. I'll also add, if you're familiar at all with MITRE ATT&CK or the MITRE ATT&CK Evaluations Project, I lead all red team activities from development to execution of our different adversary scenarios. I'll also share with you I'm very much an academic. Currently, I'm a PhD student. I'm studying cyber operations with Dakota State University. Right now, I'm actually taking an advanced malware analysis class. So most of my evenings are occupied with an insane amount of unpacking and deobfuscation. Now, when I'm not inundated with school, I also try to give back to the community. You can see some of the different projects and conference events I've supported in the past. If anybody's going to be tuning in to SANS Pen Test Hack Fest, I'll be presenting there just next week. And I'll say whenever I find I need a break from staring at terminals all day, I do try to get outside and do some volunteering. That photo on this slide was taken just 2 weeks ago at a volunteer tree planting in Baltimore, Maryland. All right, so with introductions out of the way, let's start getting into some of the substance of this presentation. So when we think about it, we might ask from a high level, what is adversary emulation? What does this have to do about with implementing adversary TTPs? So basically, adversary emulation is really about executing real world adversary TTPs, usually with the goal of assessing and improving cybersecurity. Now, let's unpack TTPs a little bit for those who may not be familiar. So, TTPs in this context basically means tactics, techniques, and procedures. It refers to those high level goals that the adversaries are trying to achieve, the specific techniques they use to achieve those goals, and the procedures, basically the implementations for realizing those goals. Now, the reason we want to emulate real world adversary TTPs is so that we can assess and tune our defenses against adversary behaviors. This is in contrast to fragile signatures or assessments that are not necessarily representative of real world threats. Right? So that's basically adversary emulation and TTPs from a high level. Now, it's all well and good to emulate real world TTPs to assess and improve cybersecurity. But where do these TTPs come from? They have to come from somewhere. And to that I say, somebody has to implement them. Now, within my organization at MITRE, implementing realistic TTPs is one of my primary responsibilities. And as we go forward, I'm going to start to talk to you. What are some of the approaches we take to implementing realistic TTPs? And how do we balance them against constraints like limited time and budget? Bear with me. I have to hydrate occasionally. So, this entire talk is about implementing adversary TTPs without breaking the bank. So, let's first take a moment and discuss what is a TTP implementation and what does it look like? Now, fundamentally, TTP implementations are procedures for executing adversary behaviors. It's these procedures that enable us to conduct adversary emulation activities. Now, when we think about what does a TTP implementation look like, in general, they include all the resources needed to execute the TTP in the context of like an engagement, right? So it includes different things like command line syntax, any needed tools, attack mappings, and so on. Now, I'll say that it's perfectly fine to implement TTPs individually. But at MITRE, we typically implement our TTPs in groups that are chained together based on how the adversary has acted in the past, usually with the goal of trying to emulate a specific adversary campaign. I'll also point out on this slide, we provide a graphic that illustrates what our TTP implementations look like. I'll also add, if you want to see these TTP implementations in the context of an adversary emulation plan, these are freely available on our GitHub repository. You can see the link on the bottom of my slide there. And if you're curious, you could find it by Googling the seated adversary emulation library. And within that project, you'll find full adversary emulation plans that shows these TTP implementations in the context of an emulated adversary campaign. Right. So summarizing all of this, this is basically what a TTP implementation looks like. So let's now shift gears and start talking a little bit about the problem statement. So we understand adversary emulation is about executing real world adversary TTPs. We also have a general understanding as to what those TTP implementations look like. And again, that's our procedure for executing adversary behaviors. So, what is the core problem that this presentation is trying to address? Basically, as adversary emulation engineers, we want our TTP implementations to be representative of real world threats, right? We're trying to emulate realistic adversaries. Further to that point, we want our emulations to be as close to the original TTPs as is practical for our particular project. Right. And I'll be the first to say you're never going to get something that is 100% identical to the original specimen seen in the wild. Really, what we're focused on is emulating those core behaviors that generally don't change across adversaries, changing fragile signatures, maybe altering their tools. Now, as much as we're trying to perform realistic adversary emulation, we fundamentally need our TTPs to be cost effective and timely. And this makes sense. We can't spend a year trying to come up with the perfect emulation, say APT 29 during the SolarWinds breach. You could spend an indefinite amount of time trying to get that right. We know our budget and our time are finite. So we have to find that happy balance where we have TTPs that are representative of the emulated adversary, but at the same time, we can deliver it on time and within our budgetary constraints. Right. So that's basically the problem statement that this presentation is exploring. So when we talk about adversary emulation, implementing TTPs, balancing time and cost, fundamentally, this is an exercise in balancing trade-offs. Now, on this slide, we kind of show what those three core trade-offs are from a high level. It basically boils down to quality, time, and cost. So let's try and unpack those constraints a little bit. When we're talking about quality, we're really asking what makes a good TTP implementation? And you could come up with different things based on your project requirements. But these are the basic characteristics that we typically see at MITRE within our own projects. Like, first and foremost, we want our TTP implementations to be realistic. It has to be representative of real world adversary behavior. Further to that point, we want our TTP implementations to be safe. Or more specifically, we want it to be something that we can execute in a controlled manner. For example, we don't want to emulate ransomware TTPs and have it worm out of control. It has to be something where operators are in control of at all times. We also want our TTP implementations to be maintainable. Ideally, those are TTPs that we can reuse across multiple engagements or that we could extend and alter as our project goals and needs change over time. We also want our TTP implementations to be easy to use. For example, if you're trying to implement some really complicated malware, you can find yourself in situations where your TTPs might be really hard to build or to utilize by non developers. So we make it a point to make our TTPs as usable for non developers as possible. So, taking all of these characteristics into consideration, these are typically the things that result in a high quality TTP implementation. Now, the challenge with this level of quality is that it is very much time and cost intensive. You'll find that for a given project, we inevitably have a date when our TTPs need to be ready to execute. So, inherently, that means that we've got a fixed amount of time to develop and implement those TTPs prior to an engagement. Additionally, we know that for any given project, we do have a finite budget. There's those expenses that are basically the cost of doing business, your operating expenses. Those are things like keeping staff on payroll to ensure that we can actually get the job done. It's also worth considering that if we develop our TTPs with reusability in mind, they actually could become something that can generate value after the initial cost of development. So, in that sense, you can look at TTP development as a capital expense. Again, that's something that you have to pay for up front, but it could potentially deliver value later on down the line, particularly if you start reusing these capabilities for more development, for more engagements. So, let's take a step back. We have these three constraints that we're trying to balance in adversary emulation: quality, time, and cost. Something else to consider is that these constraints are often mutually exclusive. As an example, you can implement high quality TTPs really fast. The trade off is you're likely going to pay significant costs building a large team of highly paid experts. As another example, you could try and make TTPs really, really fast on a shoestring budget. But in that case, you're likely going to find that quality is severely lacking. So these are some of the constraints that we have to wrestle with. And when we're talking about implementing realistic adversary TTPs, we have to try and find some happy medium within our project constraints so that we can achieve success. Now, as we go forward in this presentation, I'm going to share with you some of the different approaches and techniques that we use to try and balance these constraints. So, this might be stating the obvious, but to effectively balance our different constraints, we really have to spend some time doing thorough planning. Now, there's usually three questions I ask early in advance of any adversary emulation project. Excuse me. So, one of the first questions I'll ask is, what specific problems are we trying to solve with this adversary emulation project? And the thought process there is we don't want any effort going to things separate from those core problems because it's potentially wasted effort. Next, I want to know, how much time do I have to implement the TTPs? And what is my budget? Because that tends to influence how big my team can be for a particular project. Right? So we've got our objectives, we've got our time and our budget. Lastly, one of the things I want to know is, how do we measure or define success? Is your adversary emulation project supposed to deliver a quantifiable return on security investment? Or maybe you're doing adversary emulation in the context of some kind of security consulting. And in that case, your success might be measured on how many dollars of revenue you generate as a result of using these different TTP implementations. Now, I would assert that these questions are tremendously significant because the answers directly inform our approach to implementing adversary TTPs. For example, we can choose to emulate TTPs using existing tools. We can use original malware. And more on that subject later. I've got some strong opinions on that. We can also choose to create custom tools or unique tools to solve our specific problems. And then finally, there's the combination of approaches where maybe we're trying to mix existing tools, original malware, custom tools in the context of an engagement. Now, the bottom line is in order to know which approach to pick for our project, we have to know what our time, cost, and quality constraints are. So, what I'd like to do as we go forward is we're going to explore some of those different approaches to implementing adversary TTPs. And specifically, we're going to try to discuss how these approaches can influence our quality, time, and cost constraints. So, let's begin with using existing tools. Essentially, this approach means we're emulating adversaries who are using tools that are either native to the environment or perhaps readily available off the shelf. Right. So, some examples if we're thinking of adversaries using living off the land binaries, it's those usual utilities like task list, netstat, and so on. It can also include those off the shelf tools, things like Mimikatz, Metasploit, or Cobalt Strike, just to name a few. Now, on this slide, I've included a graphic. This was created recently by Sophos, and you can see it in their 2022 threat report. This graphic shows the prevalence of common attack tools seen in the wild. And we could see that Mimikatz, Metasploit, Cobalt Strike do rank as some of the amongst the most prevalent tools that they're seeing on target on like a per host basis. So what I find interesting about this is if we study this diagram in detail, we can actually see that all of the tools are trending downward. And that kind of makes me think that adversaries are likely pivoting to other tools. So, at least for now, there's still a lot of value to be found by emulating these different tools, but we'll likely see that evolve as time continues. Now, I would assert that using existing tools is a really great entry point for adversary emulation, right? So, if you're looking to stand up an adversary emulation program, this could be a really good starting point because, in general, this approach is low cost. It takes a low amount of time to implement. And it's easy to understand why this is the case. Because when you're using existing tools, obviously you're not spending any time developing new tools. You're just taking what's already available in your likely in your environment and applying it in the context of adversary emulation. Now, with this approach being relatively fast and cheap, it does have a trade-off, and that trade-off tends to be quality. To give you some examples, maybe you're emulating Mimikatz for the umpteenth time in an environment, and you'll find that there's likely minimal value because nearly every security product lights up like a Christmas tree whenever Mimikatz is executed, right? So you're emulating behaviors that are likely mitigated by existing security solutions. The other thing to consider, though, is maybe you execute Mimikatz and it succeeds, it runs successfully. In that particular case, the return on security investment is really, really large because you just mitigated a very prevalent TTP. But it's also important to realize you've only come this far, you still have that much further to go. So, with these different examples, it kind of reiterates why I think using existing tools is a good entry point for adversary emulation. In general, it's fast, it's cheap, and that also means that the bar for generating value is fairly low, so it's not overtly difficult to generate a meaningful return on security investment. Now, the next approach I want to talk about is using original malware for adversary emulation. Now, this is a pretty interesting approach. At a high level, we're talking about using original malware to emulate specific adversary TTPs. And of course, that is the most authentic way to emulate adversary behaviors, right? Because these are the original adversary TTPs that were observed in the wild. So, on the one hand, you get maximum authenticity or realism, but it does come with a very significant cost, which is safety. Now, in my job, I seldom use original malware unless I have complete 100% understanding of that malware's capabilities. Right? Because what network owner would sign off on a red team using original malware in their production environment if that red team did not at least have 100% understanding of how that malware would behave in the environment? Now, gaining a complete understanding of original malware basically requires either source code or extensive reverse engineering. Now, if you take a look at the images on this slide, you can see there's a screenshot of source code. This was taken from the original Carbonac malware, which was discovered by analysts from FireEye. You can see this Twitter post is from Nick Carr, and he states their team spent 500 hours analyzing over 100,000 lines of source code. Can you imagine being in a similar situation in an adversary emulation project? Given the scale, what is the probability that you will miss something like some critical understanding about that adversary malware? You then bring it into a production environment and it causes significant damage. In that case, clearly there's a huge cost to your return on security investment. So, all that is to say, using original malware, yes, it is the most authentic TTP implementation, but there are serious safety considerations that we have to be aware of if we're to use this in an adversary emulation project. So, to give you some tips or rather some thoughts here, I'm only ever comfortable using original malware really for specific kind of tests or engagements. A good example is assessing security products in an isolated environment, right? Doing things like detonation chamber type assessments or research. Definitely not doing that in production. If we're talking about production networks, typically what I'll do is I'll look at the original malware in a controlled lab environment. I'll do some level of reverse engineering and malware analysis to understand what do their TTP implementations look like at the lowest level. With that knowledge, it will directly inform how we implement our TTP. So, in other words, we're studying the malware in a lab. We're then implementing those TTPs in our own trusted specimens, of which we have written the source code. We have maximum confidence that it will only do those behaviors that we want to emulate in production. Now, based on this discussion and these different examples, I would assert that using original malware safely is really, really slow. Think back to Nick Carr's reported 500 hours, 100,000 lines of source code to understand this subject malware, right? This inherently means that the cost is also very high and the quality is variable. If you run original malware and it ends up wreaking havoc in a production environment, the quality is low because you've just lost all value from return on security investment. On the other hand, it can shift the other way. If you're doing very particular testing, like researching in a isolated lab environment, the return on security investment can potentially be high. So let's now start talking about using custom tools for adversary emulation. So basically, this approach entails using your own tools, or rather creating your own tools based on known adversary behaviors. Now, to share with you some anecdotes, I find that sometimes, or rather some examples, I find that sometimes this approach is the only viable option for implementing a really unique or sophisticated adversary TTPs. If you look at this diagram on this slide, this was a screenshot taken from the MITRE attack framework. And on it, you'll see some really sophisticated TTPs that have been observed in the wild by a variety of different actors. Right? If you skim through this, you'll see examples like adversaries using encrypted virtual file systems stored in the Windows registry. We got another one here, hiding bootkit components in unallocated disk space. Last time I checked, I haven't seen these capabilities in common tools like Metasploit. So if we're trying to emulate these kinds of TTPs, likely our only option will be implementing our own version. So let's unpack using custom tools a little bit more. Using custom tools can bring great value, particularly when you have unique requirements. For example, if you're trying to emulate some of these advanced TTPs, the return on security investment can be really, really high because you're not going to see a lot of mainstream red teams running these kinds of techniques. So the return on security investment can be high, The other thing it can do for you when you're using custom tools, it lets you try and focus your analytics, your detection on behaviors rather than the tool. To unpack that a little bit more, let's suppose you're using Metasploit. Maybe you're using Meterpreter to model specific behaviors. What you'll likely find is because the fact that you're using Meterpreter, most security controls will identify it and block it pretty much immediately. So in that case, you're kind of skewing your analysis to the tool rather than the behavior. When you're using custom tools, that's basically a non-issue because we're talking about tools that have never been seen in the wild. The different security controls don't necessarily have any biases or analysis on that tool at the time of first use. Now, of course, while using custom tools can have a great return on security investment, the trade-off is typically time and cost. Implementing custom tools inherently will take longer than using existing tools, like just copying and pasting commands for different living off the land binaries. With this additional amount of time, the cost is inherently higher. You've got to pay for developers to implement these different adversary TTPs. And if we're talking about behaviors like these advanced TTPs featured on this slide, you basically need experts on staff in order to implement those TTPs. Right? So when it comes to using custom tools, upfront time and cost is typically high. Now, in a little bit, we're going to shift gears and I'll start talking about some other approaches to driving down time and cost, particularly as it relates to implementing custom tools. Let me see how I'm doing on time here. Now, on this slide, I wanted to show you how different TTP implementations and approaches compare at a glance. Now, keep in mind, throughout these past few slides, I'm fully aware that these are generalizations. You can likely come up to examples that don't perfectly adhere to this roll-up. But in my experience, I generally find that these different figures of time, cost, and quality, this is usually the case. Now, we talked about existing tools. They can likely deliver the greatest return on security investment, particularly for organizations with less security maturity. So again, if you're looking to stand up an adversary emulation program or capability, starting with existing tools is likely where you can get the greatest momentum at the lowest cost early on. We talked about using original malware. And I generally don't advocate for using original malware for adversary emulation unless you are fully prepared to accept the risk that entails. And typically that means either getting 100% understanding of that malware before you introduce it to production, if you introduce it to production at all, or on the flip side, using that malware in a controlled, isolated environment for specific kinds of testing. Now, we also talked about using custom tools. And I think that this is a logical next step to take after you've exhausted the value from existing tools, right? So maybe you've reached the limits of what you can get by emulating things like Mimikatz, Cobalt Strike, or Metasploit. At that point, it might be a good transition point to start using custom tools, implementing specific adversary TTPs to see if your defenses can, in fact, identify those behaviors rather than getting biased on some of those off-the-shelf tools. So we talked about the different approaches to implementing adversary TTPs. We also talked about their inherent time, cost, quality trade-offs. As we go forward, I'm going to start talking about, let's assume we're doing all these things. What are some additional steps we can take to further drive down time and cost to implement these different adversary TTPs? Now, at a high level, we think about how can we drive down those costs? Generally, my answer is to focus on implementing your TTPs with reusability in mind. Let's talk about that in greater detail. So when we talk about implementing reusable TTPs, basically we're talking about TTPs that we can reuse across multiple engagements. And it kind of, it's intuitive to think that you spend the time and money to implement TTPs once. If you continue to reuse those TTPs across multiple engagements, then you're generating additional return on security investment. And in that case, the more you use these TTPs, the more it will start to counterbalance whatever that initial cost of development and implementation was, right? That's why we could view that as more of a capital expense as opposed to an operating expense. But that is only true if we are in fact rebuilding our TTPs to be reusable. If, on the other hand, we implement TTPs that are used once and we throw them away, well, that was a lot of effort that went into that TTP implementation, and you'll never see any additional value from those TTPs. Right. So that's kind of what it means to focus on implementing reusable TTPs. Now, speaking from my experience at MITRE, we talk about what do reusable TTPs look like? What are their common characteristics? It's usually some combination of these. Generally, our TTP implementations are built from clean and flexible source code. We typically document our TTP implementations, everything from documenting the source code to documenting procedures. How do you set up an environment to run these different TTPs? What is the exact command, syntax, and guidelines for executing these TTPs in the context of an engagement? That all kind of traces back to having clear documentation. And then lastly, we try to automate all aspects of our different TTP implementations, everything from automating builds, unit tests, execution, and so on. So those are some of the high level characteristics that our reusable TTPs follow. What I'd like to do as we start to go forward is let's zoom in on these different approaches to implementing reusable TTPs, and we'll provide you real world examples that we've applied in the workplace to kind of exemplify these different characteristics and ultimately drive down the time and cost it takes to implement realistic adversary TTPs. So we talked about the importance of clean code for reusable TTPs. Obviously, we know if the source code is clean, it is far easier to maintain, reuse, and change that code for follow on adversary emulation projects. One of the things that we do pretty regularly in attack evaluations, we absolutely draw source code from our previous TTP implementations. And in that way, it reduces development time and effort. And it's easy to kind of understand why this is the case. On this slide, you can see a couple of examples. On the left, we have a TTP implementation from APT 29. And I'll point out that you can see URLs to these different TTP implementations featured on the slides here. So back in 2018, we implemented this APT 29 based malware. And at that particular time, it was a non-trivial amount of time and effort to implement this particular TTP, but we were generally happy with it as being representative, authentic of those different behaviors that were under test. So we spent all this time and effort back in 2018. By the time 2019 came around, we were focused on implementing TTPs to emulate the Fin7 actor. And if you're unfamiliar, Fin7, they're a financially motivated type of cyber actor focused on compromising organizations like hospitality, payment card organizations with financial theft is kind of one of their core goals. Right. So in 2019, we're trying to emulate different Fin7 behaviors. And based on CTI, we were studying some different malware specimens. In this case, it was the Pillowmint specimen of malware. To tell you a little bit about Pillowmint, this is kind of an interesting malware specimen. Basically, what Pillowmint does is it's malware that will iterate through process memory looking for credit card information. So basically, it's an in-memory, or rather, it's a credit card skimmer that tries to get credit card info from memory. So compare that to our APT29 implementation. The APT29 implementation was basically a traditional RAT, an implant that just calls back, sends a shell to a control server. With this Fin7 implementation, we were trying to implement credit card skimming malware to model that particular threat. So this is a good example where we have two unique TTPs that we're trying to implement, but we were able to draw from the same source code. On this slide, you could see that with our APT29 implementation, we were trying to iterate over different processes using API calls like create tool help 32 snapshot, process 32 first, and so on. So we had this APT29 implementation, and it served as a very helpful reference to implement our Fin7 emulation of the Pillow Mint malware. So the only reason we were able to do that is because we maintained our source code. We generally kept it clean, and we had a good understanding of it. So that enabled us to implement a new TTP in a significantly reduced amount of time compared to the original APT29 implementation. Right. So in order to implement our reusable TTPs, we want to keep clean code as one of our design priorities. So the next one I want to speak to is clear documentation. On attack evaluations, our red team procedures are thoroughly documented and they show exactly how to execute emulated TTPs. I'll point out that our adversary emulation plans and these procedures are publicly available on our GitHub. You could see the URL there. It's the same project for most of these screenshots I've been showing throughout this presentation. So if you want to see examples of what these procedures look like in their entirety, you can check out those hyperlinks referenced in this presentation. Right. So getting back to clear documentation, fundamentally, we document everything from our source code to our build processes to our execution procedures. Now, it's the execution procedures that are particularly important for driving down the cost of time and development. Basically, what these give you is they enable non developers to execute adversary emulation plans. Right, because if we circle back here and you see this source code, this was written in C++, and that's a non-trivial programming language for just any cybersecurity practitioner. You can't realistically expect every cybersecurity practitioner to do this level of systems programming. So by having written procedures like this, we kind of drive down the barrier to entry so that we could have other employees, non-developers, execute these adversary emulation plans. And when we have staff repeatedly executing these TTP implementations, they will generate additional value. And we know that that value will eventually counterbalance the initial development costs. Right. So by having these clearly documented procedures, we make it really easy for non developers to execute our adversary emulation plans. And with that, you generate more value to offset the initial development costs. Now, one of the other things we make great use of is automation. Pretty much in attack evaluations, we try to automate everything we can. We automate our source code builds, our unit tests, and even execution. Now, this has a lot of benefits. When it comes to automating source code builds, you never want to manually build projects. It's easy to spend 5 to 10 minutes. If you've got some C++ code written in Visual Studio, easy to spend 5 to 10 minutes logging in, opening Visual Studio, making sure the right settings are configured, clicking the build button. That's really tedious. I like instant automated builds. If you're familiar with like Linux-based build processes, I like to just type the make command and it automatically builds my project. So we do make use of automated builds, either using things like make, CMake, whatever build system we happen to be using for that particular language. We automate the build, and that basically makes it so that we don't waste time building projects as we go forward. We can then devote that time to other more interesting things like implementing specific adversary TTPs. A side effect of this too is when your code is always building, you generally have a little bit more confidence when it comes to making changes. You can make changes if your source code still builds, you didn't break anything, presumably you're moving in the right direction. Excuse me. The other thing we automate is unit tests. When you're emulating really sophisticated adversary behaviors, your code bases could start to get large. When you start getting into thousands of lines of source code, you might find yourself going down a path where you make changes in one section of code that breaks functionality elsewhere in your code base. And obviously, when you do that, you have to start spending time debugging, and that can be really wasteful. So what we do in attack evaluations is we make use of unit tests. We have automated unit tests that, with reasonable confidence, prove that our source code functions the way that we intend it to do so. And again, that just puts you in a better position to make sure that your code is always buildable, that it's always ready for production use. And if at any point your requirements change, your project goals change, because you have this architecture in place, you're much better postured to respond to changes if and when they come up. The other thing we try to automate is execution. While I don't have it featured on this slide, if you were to go to our CTID Adversary Emulation library, you can actually find our procedures in YAML format. So it looks just like this, except it's in a YAML document, and that could be ingested by different frameworks that kind of emphasize automated execution. We specifically support MITRE's Caldera framework, but the takeaway there is that it could ingest one of these procedures in YAML format and then execute it in an automated manner. So obviously, once you get to the point where you can execute these adversary TTPs in an automated manner, you're free to kind of reduce whatever your staff overhead looks like for that particular project. It also kind of sets you up to use these things as like a leave behind capability. For example, one of the things we might do is we might do an engagement that is human driven. But when the red team is done with that engagement and they move on to other things, we'll leave behind something like Caldera and automated implementations of our adversary emulation plans. In that way, the network owners could continue to run it in like a continuous assessment kind of context. Now, one thing I'll emphasize is that anytime we talk about automating red team activities, there might be some red teamers who get a little bit worried about the prospect of automating themselves out of a job. And I know from my experience, that's pretty much seldom the case. We always have a need for human operators, either to be in absolute control, particularly in high risk or environments where you just need to have really granular control. And there's always going to be a need to do additional research and development for these different adversary TTPs. So I've never really been concerned about automating red team out of a job. If anything, it's just another tool that kind of helps us cope with significant demand for the kinds of things that we do. So that brings us to the summary of this presentation. So let's kind of reiterate some of those key ideas that we discussed. Basically, we talked about implementing adversary TTPs as being an exercise in balancing trade-offs, namely time, quality, and cost. We talked about how effectively balancing these trade-offs requires an understanding of your available time, budget, and your engagement objectives. How do you define success? And with those in mind, you always want to make it a point to plan and understand those constraints before you start actually implementing adversary TTPs. We then explored different approaches to balancing these trade-offs. Everything from emulating adversary TTPs with existing tools, maybe using original malware, or writing custom tools, perhaps to emulate some of those more sophisticated techniques you don't get from off-the-shelf tools. As we compared those different trade-offs, we established that in general, using existing tools is typically more cost-effective, particularly for organizations with low security maturity. So using existing tools is likely a good starting point for organizations looking to stand up an adversary emulation program. We also talked about how you might consider implementing custom TTPs after you've exhausted the value from existing tools. After kind of comparing those different approaches, we offered additional tips to kind of driving down time and cost while still sustaining quality. And that basically boils down to implementing TTPs with reusability in mind. You know, by keeping your source code clean, having your procedures documented so that non-developers can execute your implementations, and maximizing automation so that your capabilities are always production ready. You're always ready for the next engagement. When you take the totality of these different techniques, you find that you could drive down the time and cost it takes either to implement these TTPs or offset that initial cost so that you can get significant returns on security investment as you go forward. So that brings me to the final slide. So this is the end of the presentation. I hope you found some of these examples and stories interesting or at least informative. I'll say on this slide, I do have my contact info listed. So if you have any questions, comments, or just want to chat, you're welcome to reach out to this information here. Otherwise, I'll say thank you very much for dialing in and listening. I'll also say thank you very much to the Adversary Village for providing the opportunity for me to present. So, with that, I'll go ahead and turn it back over to the Adversary Village moderators.